Dr. Candace is a professor of statistics and the associate chair of the Department of Statistics at Brigham Young University. Her research interests are in Bayesian modeling, spatially dependent data, and environmental application of statistics. She's actively involved in many statistics associations, including ASA's section on statistics and the environment, and ISBA's section on environmental science. Let's welcome Professor Candace to the podium, please. Let's clap our hands. Thank you. Welcome, Professor.
Thank you so much. I feel really privileged to be here, and I really appreciate the invite. And I'm excited to learn from you and to share with you a few things that I know as well. The presentation is mostly meant to be kind of as a presentation. I didn't know how well I could do an interactive kind of R session. So I made these slides with R code in them, as well as kind of like some motivating principles behind geostatistics. And then I'll share them with Joseph afterward, and he can send them along as well. Okay, so just a little outline of what I'm going to talk about today. First, I'm going to talk about the different types of spatial data. Then we'll kind of talk about thinking about spatial dependence and some different things to consider when thinking about spatial dependence. Then I'll talk about some common geospatial analyses in R, and then we'll talk just briefly about accommodating large data in R. And I'll kind of give an overview of some packages that are available to accommodate large geospatial data. So first, the types of spatial data. So the first type, and the type that we're going to be talking about today, is called geostatistical data or point reference data. And this is data that corresponds to a specific location. For example, in this picture, I have PM 2.5 measurements at a specific latitude and longitude. So the location is fixed, it's not random. What's random is the PM 2.5 measurement. This relates, so my applications are usually in environmental or health data. And so those are the applications that come to my mind really quickly, but it's also common in business settings. If we have company data where how much is being sold at different stores and things like that. So this type of data is very common. And what we can see from this PM 2.5 plot is that higher PM 2.5 values are right here in the Midwest of the United States, kind of medium here in the Southeast, and then higher or low and high levels here in California. And so definitely there's some spatial dependence there that we see common behaviors in spatial areas, but kind of modeling that and trying to interpolate or determine relationships, there's lots of ways to do that. So we're going to talk about that today. But I want to talk about a couple of other types of spatial data. The other common type of spatial data is called aerial data. Usually this is data that corresponds to a region, for example, a county or a state. And again, just like with geostatistical data, the location is given or fixed. This usually comes with like demographic data. So what I have plotted here is the county regions in Malawi, looking at this kind of all injure measurement, and it's a measure for the whole region. So it's not measurements at a specific point like the geostatistical data, but it's measurements over an entire region. The third type of data is called point pattern or point process. This is where the location is random. So rather than the location being fixed and the measurement being random, the location is what's random. Here I have plotted in cases of infant bronchiolitis in Norfolk, Virginia, and this is like where it's occurring. And so we might be interested in like in ecology, like keeping track of where birds appear. And so Birds could appear in different ways spatially than other breeds of birds. And that's kind of where the point process approach comes in. So being aware of the 3 different types of spatial data can help determine which direction you want to take when you're doing your spatial analysis. So not all spatial data are going to fit into the geostatistical framework that we're talking about today. And so I wanted to give an overview of those 3 different methods just so that you're aware of them and can look into other fun methods at another time. So there are many, 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 many spatial packages available for R. R has a nice list of spatial packages at this website here. The packages that I'm going to use today are the GStat package. That's the one I'm going to focus on most. I'm going to make use of the SP package. This helps organize spatial data. And then I'm going to use the NLME package. This will fit some generalized least squares models. Also, I didn't load them right away here because there's some competing functions. So this spatial package, it comes with R, but it has its own spatial functions that conflict with GStat. So I didn't want to load it already, but I'm going to look at it. I'll mention SPBase and then some kind of packages that handle bigger spatial data. I'll mention those as well. And then I really like this R color brewer for different colors, but some of these packages have their own plotting methods that I use. All right, so first thinking about spatial dependence and how do we model that? How do we quantify that? So I have a little illustration here. These circles represent points in space along a horizontal line, and then the color of them represents the measurement that we're interested in. So like I showed PM 2.5 earlier, we're going to look at zinc measurements later. But it could be kind of whatever it is that you're measuring. And one of the core geostatistics principles is that measurements that are close to one another in space are more similar. So these first 2 circles are close in the space, and they're more similar, they're more blue, more the same color than measurements that are farther apart. So the farther away we get from that first blue point, the more dissimilar we get from that blue point. So it gets red. And this is like what kind of drives geostatistics modeling and all of the approaches that we take. So just to reflect back to kind of intro probability, when we first learned about probabilities on events, we learned about conditional probabilities and marginal probabilities. So let A be the event that circle 1 is blue. So I'm talking about this illustration. So this first circle, the event that this is blue is called A. And then we're going to let B be the event that circle 2 is blue. So this will be circle 2. And we want to let B be the event that that circle is 2. When A and B are independent, then the probability of A is equal to the probability of A given B, meaning that knowing B doesn't give us any additional information about A. But since we have this nice core geostatistics principle, knowing that circle 2 was blue and that it's close to circle 1 actually should increase the probability that circle 1 is blue as well. And so how we would write that using probability notation is that the probability of A given B should be greater than the probability of A. In fact, we know we can use this to estimate an entire probability distribution about circle 1 being any color. So maybe before we collect data or before we know what circle 2 is, we have, I know that the color is going to be anywhere from blue to red. And so kind of my best guess would be the average or purple. But then after I collect the data about circle 2, I have information and that it's close to circle 1. And so I have a better guess about what the probability is that the circle 1 is blue. So this is what's driving all of the methods that we're going to talk about. And then we will kind of get into how knowing this terminology can be helpful as we're fitting these things in R. So we're going to let y be the random variable of interest, so PM 2.5 measurements or our zinc measurements, and it's going to be measured at different locations SI. And we either want to predict or quantify relationships with other variables. So I think one of the most kind of gratifying things that we can do with geostatistics is to make a pretty interpolated plot. But it's not just to be able to predict at unobserved locations, but we also want to appropriately account for uncertainty about those predictions. So we're estimating the expected value of y as well as the variance of y. And we want to get that variance right so that we can have better predictions. Because we have this dependence, we can actually decrease our uncertainty of y because of that spatial dependence. So we make use of that dependence to help inform our predictions. This was kind of that principle that the probability of A given B increases as if we know B. So the other thing that we might want to do is quantify relationships. So often I really love to think about regression. So if we think about our regression equation, y equals x beta plus some epsilon term, we might want to learn about beta. And so our quantifying or understanding relationships really comes in estimating beta, the expected value of beta, and then our uncertainty around beta. However, in this case, spatial dependence doesn't decrease uncertainty. Spatial dependence increases uncertainty because we have less information from these points because they're dependent on one another. And so kind of thinking about, well, what's the problem that I'm hoping to solve? Am I focused on prediction or am I focused on understanding relationships? And the approach that you take is going to be different depending on which approach you're looking at. So just some questions to think about as we think about spatial dependence and how we want to quantify spatial dependence. So the first question is, how do we quantify these similarities? How do I quantify the fact that these two are closer to the same color than these points that are farther apart? I think one way that might kind of come to us right off the bat is with correlation. So points that are close together are more highly correlated. They're more similar, right? So correlation is a way to think about that. And as we look at any of these 2 points that are right next to each other, they're pretty close. If we just look at just the two of them, they're all pretty similar to each other. Similarly, we could think about variances. So because they're really similar, the variance between them, or maybe the squared difference between them, is quite small. And so we're going to think about it in terms of variances. But kind of as we're going through modeling this, we can think about it lots of different ways. Another question to think about is, are the dependents, how are they similar across the space that we're looking at? So in this little example, I changed the colors. So you'll notice that these 2 points, this blue one and then this middle red one, they're very different. But if I look at 2 points the other direction on the other side that are about the same distance apart, they're very similar. So where we are in space matters how similar things are, and that distance metric matters depending on where we are in space. The third question, does direction matter? So here I've expanded my 1D example and made it a 2-dimensional example where we have a horizontal space and a vertical space. And we'll notice horizontally, the observations can be quite different, but vertically, the observations are pretty similar. So yes, there's some variation in how blue this blue is on this part, but mostly when we're looking at the vertical space, things are very similar, but in the horizontal space, they're very different. And so thinking about that direction can matter. And finally, what about accounting for covariates in space? So I added a covariate with a symbol. So the triangles maybe represent like a treatment group, and the circle represents the placebo group. And we'll notice that on the right-hand side of the plot, we have more triangles. So the triangle group is more likely to be red, whereas on the left-hand side of the plot, we have more circles. The circle group is more likely to be blue. And so are we observing spatial dependence, or are we observing just a covariate effect? And so we want to account for those covariates. Okay, just a little bit of notation, just a very general spatial model. So we have our observation at a location S, so PM 2.5, or the zinc measurement, or kind of how many products we sold at a specific location. And we're going to measure that with a mean process. Now, this mean process can be an intercept, so it can be constant everywhere. It could be dependent on latitude and longitude. That's often important when accounting for environmental variables. Or it could be an X beta, so we could have a covariate in there. The first case we're going to consider is just a constant. So this mean process is just the same for all locations. Then we have this spatially dependent error term. And this is where we say, hey, all of Y, all of the dependence that we're seeing in Y, that spatial dependence that we're seeing in Y, is coming from omega. And then we have a noise term, which is our typical regression error term. We often call the variance from this term a nugget. So we're interested in understanding this spatial process, omega, and we can model that with a normal distribution with a mean 0 and then a covariance structure sigma. But how do we define sigma, right? So those questions that I was looking at earlier were to motivate this sigma and how we're going to pick a sigma and how we might want to model that covariance term. All right, some common geospatial analyses in R. So some ideas for sigma. We may want to model the correlation or the covariance between two locations using the distance between the locations. So because of this spatial dependence and this core principle that things that are closer together are more similar than measurements that are farther apart, we expect that variance is smaller for values closer together and then gets larger for values that are far apart. We also would expect that the variance levels off at some point. So it doesn't matter how far I go beyond this distance, the variance kind of stays the same just because there's no more dependence after that point. Other common assumptions is this stationarity. So no matter where we are in space, the covariance or the correlation is the same. So I motivated that with just that horizontal where we said, oh, look, the correlation would be different for those 2 points than these 2 points on the other side. And then isotropy, which is that directional component, that no matter the direction, the covariance will be the same. We're going to assume those to begin with, and then I'll show you guys towards the end some ways to accommodate lack of stationarity or non-stationarity, and then a lack of isotropy, which is anisotropy. Okay, so one thing that I like to do is to visualize this spatial dependence. And a common way to visualize this spatial dependence is to use this variogram. So the idea is to take all sets of points that are a distance h apart, and then we're going to take the average of their squared deviations, and then we'll divide it by 2. So it's actually called the semivariance because we divide by 2, and that just has been shown to be more stable when we're estimating the variogram function. And then we're going to plot them, and then we can see if these assumptions that I talked about on the last slide, this variance leveling off, variance is smaller for values closer together, stationarity, isotropy, we'll plot them and we'll see if that holds. Now, often locations aren't all exactly h distance apart. And so we allow for some tolerance. We'll say, so I'll show you on the next slide. So here for our little horizontal toy example, we have the distance is 0.44, but these points aren't exactly 0.44 apart. Some are a little bit closer than 0.44 and some are a little farther than 0.44. So we're allowing for some tolerance. And I've used arrows to indicate we're looking at these 2 points because they're 0.44 apart. We're going to take the squared difference of these 2 points because they're 0.44 apart, etc. And we compute that semivariance and it's 0.012. So I'm just going to plot it right here. Then we'll do it for another distance. So I didn't draw all the arrows this time, but all points that are approximately 0.89 apart, which means about 2 points apart in this little toy example. We take their squared difference and compute the semivariance and it's 0.047. And then we do it for the next distance, 1.33, plot the semivariance, next variance, 1.79, etc. All the way until we have the last distance, the biggest distance possible. One thing to notice is that the biggest distance, there are only 2 points at the biggest distance. So we aren't averaging over anything. We're only just computing the square difference between those 2 points. So all of these other points had multiple points that we were averaging over. And so that's something to consider when, we don't want to weight that point right there as much as we're weighting the points down here that have more pairs. Okay. So we have what's called variogram models, where we say, well, I think that as distance away from each other, as the points increase in distance away from each other, the variance is going to increase, but it's going to level off at some point. And these are common terms that are used in spatial modeling. So we have the sill, which is the variance, where the variance levels off at. The nugget, which is how much variance is there at points that are at measurements that are at the same point, that are 0 distance apart. So this is that error, that epsilon, the variance from the epsilon. And then the range is how long before that variance levels off. And here with this exponential variogram, we're saying that the semivariance decays exponentially as distance increases. So for this example, the range is about 15, the sill is about 0.6, and the nugget is about 0.1. And then there's something called the partial sill, which we're going to see in the example that we use, which is usually the difference between the nugget and the sill. So in this case, the partial sill would be 0.5. Sometimes the nugget is called the partial sill of the nugget, just to denote that the nugget makes up the totals, part of that total sill. So we just looked at the exponential, the solid line. Okay. But we could have other ways to model that dependence. So this dashed line is called a Gaussian dependence structure. And you can see that it decays a lot slower. And so it's going to be more smooth in space than the exponential structure is. So the dependence lasts longer. Both of these can be computed with a matern. You may have heard that term before, and it's really popular because it's more flexible than many of the other covariance structures that we use. It has an extra parameter. So a matern with the parameter kappa equal to 0.5 is equivalent to the exponential. And that's all that this slide means. And the matern with kappa equal to 2 is equivalent to the Gaussian. And then we have a spherical, which is would be less smooth in space. So it decays a lot faster. And then I just think this wave one is kind of fun to think about when we might see dependence increasing and decreasing and then increasing and then decreasing. I think it would occur in like temperature measurements that don't account for elevation or something. we don't really see it that often. I just think it's fun to look at. Okay. So this data set that we're going to look at is the MUSE data set in the package SP. It contains measurements of heavy metal concentrations in a floodplain of the River Meuse. There's a nice vignette about kriging or prediction and using computing variograms and directional variograms in the Gstat package. So vignette Gstat from the Gstat package has a lot of details written out that slides just aren't able to, you can't put all the details on slides. So what we're going to model here is the log zinc concentration in this floodplain of the River Meuse. And here we can see, here's some low zinc values along this southeast side, and then the high values here along the northeast side. And I'm not sure if it's north or south, but that's how it's plotted, I guess. So to compute the variogram, we first have to assign coordinates. So MUSE is just a regular data frame. And so we're going to use the SP package to assign it coordinates, and we're going to assign it X and Y. So MUSE has variables called X and Y that are meant to be the coordinates. And so we're just going to define a SP object by defining MUSE's coordinates as X and Y. Then we'll use the Gstat package to compute the variogram for log zinc. So that's our Y. And then tilde1. So 1 is our mu. We're fitting a constant mean across all those locations. So all the locations that we plotted here, we're going to fit a constant mean, and then the rest of the difference we'll make up for with spatial dependence. And so here we have that variogram. In this example, the variance levels off. In my toy example, we didn't have enough data for the variance to level off. But in this example, the variance levels off. It looks like the sill is about 0.6. Looks like maybe there's a negative 0.1, and then it looks like the range is about maybe 750 or something, depending on which function we're going to use to fit, whether we use the exponential or the matern or whatever. So I just wanted to print out the myvario object so we could see what's in it, so we know what it is. This is the distance, so that H, what I was calling H. So at all points that are about 79 apart, the gamma, what they call gamma, is the semivariance. So the semivariance is 0.12. And the number of pairs, so the number of pairs of points that they use to compute this gamma is 57. Then at all points 164-ish apart, the semivariance is 0.22, and there were 299 pairs of points. There are a couple other objects here, or variables here, and these have to do with the direction, which we aren't looking at quite yet. So right now we're just saying direction doesn't matter, and so that's why these variables are all just set to 0. 15 is the number of default breaks that the variogram function uses. You can go in and define it differently so that there are fewer pairs of points used to compute the gamma, or more pairs of points to compute the gamma. All of those things will change the estimation and also the fit, and what things look like for the variogram. So I would encourage you just to play around with those different options in order to kind of see, how does the plot of the variogram change if I have more than 15 distances that I'm looking at. Fit.variogram in the Gstat package will fit the variogram. So I gave it the myvario object, and then it requires this model called VGM. So the variogram is what it stands for. And then I've initialized some of the parameter values This is the initial partial CIL. This is the initial range. And then I'm going to fit it using that exponential covariance structure, and then the initial value for the nugget. This is the fit that it gives us. So it estimates the partial CIL to be about 0.71, and it thinks there's no nugget effect. So it did not estimate the nugget, or it did estimate it, it thought it was 0. And then the range is about 450. And here's a plot. So they have a nice wrapper plot function that plots the variogram as well as the fitted line for the variogram. So the line through the dots. Likewise, I could fit it with spherical, Gaussian, or the Matern. When I use the argument in the fit.variogram of fit.kappa equals true with the Matern correlation structure, then it will fit that kappa. So we're not forcing it to be an exponential or a Gaussian, but we're actually letting it estimate. And in this case, it looks like it's something in between the exponential and the Gaussian. This is the spherical estimate. I just plotted all of these the same way I plotted the one on the last page with the plot of the variogram object and the fits. You do not have to give it initial values, so you can just give it NA, or you can just specify. So I wrote it out 3 different ways so that you could know there are 3 different ways to fit this, but there's more than just 3 as well. So you don't have to give it initializations, and you also don't even have to give it an NA. As the spatial component becomes more complicated, giving it initial values is going to be helpful, and it'll give you an error if it needs initial values. All right, the plot, right? We love the maps that we get from geospatial models, and we really love that we get estimates of variance as well. So the SP package has a gridded object already for us to predict onto. I'm just going to create an SP object from the grid so that the muse.grid is a data frame. I'm creating an SP object by giving it coordinates for gridded data. They have this nice gridded function, so it can make use of gridded features. And then we're going to use the function Krieg. So a spatial prediction is often called Krieging because it was first introduced by Danny Krieg in looking at ores, bores. My words aren't coming to me. To value different mines back in 1953, I think. And then George Matheron named it Krieging after him in the late 50s, early 60s. So this is where the word Krieg comes from. And so this Krieg just means predict at the objects at the locations I want to predict at. So we're giving it the model. Remember, we're just fitting a mean structure to our Y, which is log of zinc. The data that we're using to fit it is muse. The new data that we're predicting to is muse.grid. And both of these have to be SP objects to work with this Krieg. So we have to give it the coordinates. And then the model. So the model is that variogram, the VGM. So I'm using the Matern fit. So this one right here, which was kind of a balance between all of them, but you can use whichever one you want and do some cross-validation to decide which one's best. This is when we fit just a mean at each location. We call that ordinary Krieging because of different properties that were developed. The SP package has this function called SP plot. I'm going to plot the first object from my predictions, from my Krieg predictions. And then I've just given it this title, ordinary Krieging predictions. And then I've just left the default color scheme here. And what you can see from the predictions is we're capturing the spatial dependence, which is exciting. And you'll remember when we looked, At the initial plot, we could tell that, hey, there were lower values along that southeast border and then higher values along the northwest border of that plane. And then I also think it's valuable to look at the variance. So we have higher variance at locations where we don't have data. Locations where we do have data, so we have more data up here, then the variance is lower. So our variance around those predictions ranges from about 0.1 to 0.55. That's not bad for a range of 4.5 to 7.5, but it's also not great, right? So, so maybe there's something we could do that could make it better. We want good predictions, but we also want to know that our predictions are right, or in other words, to have smaller uncertainty or smaller variance. And so we're going to look at accounting for a covariate. So one of the variables in the data set is this distance to the river mews. So the plane isn't on the river. It's a flood zone, right? So the river will come up over onto the plane. And so we have this distance to the river. And then they've normalized it to be between 0 and 1. So the distance means nothing. Now, one of the tricks here is that I'm not talking about the distance between points that we were talking about before, right? This is a covariate, which is distance to a river, not the distance between points, which is how we're modeling spatial dependence. So if we take the square root of that normalized distance to river and plot it against log zinc, we have like the most beautiful linear relationship that I've ever seen for real data. It's very lovely. So I'm really excited about that. So we're going to use the square root of distance to river as a covariate, using the same functions we were using before, but instead of fitting tilde1, so instead of fitting just the mean, a constant mean, we're going to fit it with a covariate. So before we were fitting that mu with just a beta naught, a constant mean. Now we're actually going to let account for that covariate x, or that square root of that distance to the river. So dist here is distance to the river. Everything else the same. So variogram, it's just we've changed our function to account for the covariate. We're going to fit the variogram, and I just use that matern because it's a quick and dirty way to do that. And here we have the semivariance. Now, one thing to notice, if you remember, I know it's been a few slides, but our semivariance before we accounted for that covariate was as high as 0.6. So here we've reduced the variance, which that's why we love regression, right? Regression, we account for variance using covariates. And so we reduced the variance, but we still see that spatially dependent, some residual spatial dependence. So, so we're computing, instead of the semivariance on y, now we're computing the semivariance on y minus x beta. So essentially the semivariance of omega plus epsilon. Okay, so when we account for a trend, usually it's a latitude-longitude trend. I didn't include that this time, but I just have that square root distance as a. But when we account for a trend, we often call that universal Kriging. So these ordinary Kriging predictions on the top row, are the predictions when we just fit a constant mean, right? So that first set of predictions. The universal Kriging account for that distance. Now, when we look at the predictions on the left side, the predictions look pretty similar, which is a relief, right? We don't want them to look too different. We expect them to look a little different because we fit different models. But the biggest difference that we see is in the uncertainty or the variance. We've reduced that variance quite a lot. So instead of going from 0.1 to 0.55, our variance now goes from 0.05 to 0.22, and it's a lot clearer. So the variance is smallest where we have observations, and so it's a lot easier to see where we have observations. So, and that's just simply because the variance is smaller, or so it's easier to see. The more covariates that we use, the less residual spatial dependence there should be. And so it should be easier to predict. And sometimes you can even remove the spatial dependence altogether. Instead of fitting a variogram, or in addition to fitting a variogram, there are other ways to choose what kind of spatial model you're going to use, spatial dependence structure, whether you use the Matern, exponential, Gaussian, et cetera, or a whole other approach altogether. And you can do that using cross-validation. So I have, so that the GStat package has this automatic Krieg.cv, this cross-validation approach. And again, I've gone back to the mean here. OK represents that ordinary Kriegung, and then UK represents the universal Kriegung, where we've accounted for the covariate. One of the things we can see in that ordinary Kriegung, the residuals for the ordinary Kriegung, is there's definitely some spatial dependence here that we're not really capturing. So there's some systematic things that we're missing when we only include the mean as our variable. We don't see that same level of systematic thing, missing systematic errors when we account for that covariate, although certainly we see there's bigger errors right through here. We want to see noise, right? We like it when we can get down to just nothing, no patterns. Now let's consider this directional variogram. I motivated this idea by saying, by this little toy example. In the horizontal direction, we have a lot more variability than we do in the vertical direction. So we might want to look at variograms for these different directions. So I'm going to do that for that Muse data set. I'm calling the object d.vario, so directional variogram, and they use the argument alpha to be the angles that we're going to look at. So we're going to look at the 0 angle, which is the horizontal direction, and it'll take some tolerance within that 0 angle as well. Then we're going to look at a variogram at the 45-degree angle, so northeast to southwest. Then we'll look at the 90 angle, so north to south, and then the 135 angle, so northwest to southeast. Okay, the bigger, beyond 180, it just does the same thing. So it does look like there is some difference here. So it looks a lot flatter sooner at the 45-degree angle than at these other angles. There isn't a way in the GStat package to automatically estimate that. So what they did is just provide, they just did it by eye. And so they say at the 45-degree angle, that's the maximum range. So our range comes out as far as it's going to go, whereas it seems to level off a lot sooner in the other directions. And then at the 135, the range should be 40% of the range at the 45. So that's what these parameters mean. Then the anis here, it means that the anisotropy, meaning the not isotropic, or how we're going to make these variograms not isotropic. So I just used the fit, so it doesn't automatically fit it. So I just used this fit or this definition for the covariance, and we'll predict again for those values. So again, I've gone back just to the constant mean structure just so we can compare. But you'll notice now we see these kind of patterns in the variance, this at a 45-degree angle, right? Because that's the angle that has the longest range. And so we're saying, hey, points that are in that direction of observed points, or predictions that are in the 45-degree angle of points that are observed, have less uncertainty because we have more spatial dependence in that direction. So that's what's going on right here. That 45-degree angle doesn't seem to impact the predictions as visibly, but certainly the uncertainty. I just realized I said certainly the uncertainty, and that really doesn't make sense. All right. Another package that does things more automatically is AutoMap, and they have this function called AutoKrieg. And so I just threw in the formula that we were using, the log-zinc as a function of the covariate square root of that distance to the river. Muse is the object we're estimating from, muse.grid is the new data we're predicting to, and then you can specify the covariance structure, exponential. The default plot is to plot Krieg predictions and then the Krieg standard errors. So you'll notice that these are different. The standard errors are larger than what we had found with the Gstat package, but that's because when we plotted the uncertainty from the Gstat package, we were plotting the variances. So if you square these, so the squared standard errors match up with what we found from the Gstat for the Gstat variances. So that's a nice kind of like sanity check that, hey, what we did here matches up a little bit. Now they are not going to, the uncertainty won't match exactly because we used the matern for the Gstat method that we used before, and now we're using exponential, and matern isn't an option in this AutoKrieg. And so I just picked one, and then it provides that fitted variogram, and it puts the number of points right next to how many points are used to estimate each of those variogram points or semivariances. All right, I am running out of time, so I'm just going to quickly go through the rest of the slides, talk a little bit about regression, so inference on beta. So we think about regression usually y equals x beta plus epsilon. And I just tried to keep these model notations as simple as possible, versus when we want to add some spatial dependence. Okay, but so we did this before. We predicted using this model, this spatially dependent regression model, but now I want to actually do some inferences about beta. So is X statistically significant in helping to understand Y, okay, or reduce the variance in Y? So if we just do ordinary least squares, our regular LM object, right, we're not accounting for dependence at all. And I'm just going to highlight quickly here, we have the coefficient beta, it's estimated to be -2.5, our standard error 0.155. Now, remember I said our standard error should go up a little bit because we don't have as much independent information as we think we do. So when we fit it with generalized least squares, and I'll talk about the notation here in a second, our standard error goes up from 0.15 to 0.22. So 0.15 to 0.22. So what we were expecting to happen, happened. The estimate stays about the same for beta, and given how they compute the estimates, that's not very surprising. And then we have enough data that it's significant. And man, we saw that clear relationship when we plotted it. So it definitely is statistically significant. Here are some things that you can do instead of fitting variograms. You can fit your GLS model using different correlation structures, and then choose the correlation structure based on a likelihood approach rather than fitting the variogram and then sticking with that approach. So there's lots of ways to kind of make sure your uncertainty, the choice that you're using for your spatial dependence in order to model that spatial uncertainty is being accounted for in a correct way. So we have cross-validation approaches, and then we have likelihood approaches and variogram approaches. So 3 different ways to select that correlation structure that we've been talking about. Here in this one, so GLS stands for generalized least squares, and it does more than just spatial correlations. It's in the NLME package. We specify a core spatial, and we give the coordinates here with form. We give some initial values. I didn't print out what the estimated values are, and then we tell it whether or not it's going to fit a nugget. At the Oh no, it does. It prints them out right here. So they fit the estimate for the range parameter. I initialized it at 900, but they actually estimated it to be 429, and they estimate it using restricted maximum likelihood REML approaches, which are fast and pretty accurate. And then the nugget 0.33, which I gave a value of 0.6. So I overestimated with my initial values. Spatial is a default package that comes in R, and it estimates surface products. It estimates surfaces over a box. So you give it the lower bound and the upper bound in the X direction, the lower bound and upper bound in the Y direction. So it's estimating the surface using generalized least squares. You give it the correlation structure. So exponential covariance is what I've used here. The degree of the splines that they're going to use across the space. So they're fitting a spline across the latitude and longitude. Prediction mat, standard error mat. I have plots. Again, I'll send this to you guys so you have the code. You'll notice here that so the range of the data was like from 4.5 to 7.5, but here I'm estimating from like 4.5 to 20, and that's because I'm estimating far out of the range of my spatial, of the spatial locations. So instead, I'm just going to cut the plot to a better range. There, you could overlay the spatial polygon to get kind of the more accurate places you want to predict. I just cut it off based on the times. And you can see the data, it has that same effect where points that are closer to data have less uncertainty than points that are far away from the data. So just two important notes about this. We can only model dependence for the range over which we have the data. We just saw why we wouldn't want to extrapolate beyond that data range. And then the more trends that you account for, the more likely you are to have stationarity and isotropy. And so then you can use those default covariance structures easily and more and trust the uncertainty a little bit more. Here are some functions for some Bayesian prediction. And then I just wanted to briefly go through some stuff for large data because that's becoming so common. Now, large data is definitely depends on who you are, right? So sometimes 1,000 points can be large, and sometimes 1,000,000 points is what's large. So here, there are several methods to accommodate large data sets. One of the popular and fast and kind of easy methods to think about are these reduced rank methods. So we're going to fit our spatial random error with its own regression. So it's an approximation of the spatial error, but we'll use these spatial basis functions that I call BI here. And then we'll estimate the coefficients alpha. So just like when we had X beta, we estimate that beta. Here we have B alpha, so we're going to estimate the alpha. The packages for doing that are FRK, fixed rank Kriging, lattice Krieg for lattice Krieging, and then this auto fixed rate Krieging, which I'm going to show. It does things, a few things automatically, but both of these fixed rank Krieging and lattice Krieg have some really nice vignettes to use. Fixed rank Krieging has a vignette called capital FRK _intro that goes into detail about some ways you would want to select these bases, etc. So I'm just going to show this auto fixed rank Kriging. The function is auto capital FRK, and then we're going to predict. And here are the plots. I plotted these using ggplot because that was the easiest thing to do. The range is from about 4 to 8 again, so we're getting similar predictions. The standard error is quite small, and I didn't have time to look into, should we be concerned about how small the standard error is here? Or is this model genuinely doing that much better? And I just don't know. But I thought that was a nice thing. You'll notice that the errors are more smooth though than otherwise, than the other examples we looked at. We could also plot, so here's a big data set. So I think 50,000 points, and then we're going to predict to more than 200,000 points. So I didn't actually run this in the code. I ran it before, saved the file, and then I'm plotting here. The function is lattice-Krieg from the lattice-Krieg package. Here are the observed points, and then I just predicted to these points. Now, I'm not sure if you can see this, the ranges are different. So the predicted looks different than the observed, but it's not because they are, it's because the predictions are just in a smaller range, and then the plots I have different ranges. So we're actually plotting in the range of 372 to 384 here for the predictions, which is this kind of light green to light blue range, which is what we're seeing here. So, but it's nice that we can see we have higher estimates down in the bottom of the south region of the world, and then smaller estimates in the north region of the world. One of the things I forgot to mention about these reduced rank, all of these methods for large data account for non-stationarity and isotropy. And that's just because of the way that they're set up. But that makes them better for large data sets. And so we can accommodate these. So it looks like we have kind of maybe a larger spatial dependence in the horizontal direction here than in the vertical direction here. And our model actually captures that. We have some conditional distribution approaches, SP, nearest neighbor Gaussian processes. This is a Bayesian approach. GP Vecchia is also a conditional distribution approach. Treed Gaussian processes divide the space up into independent areas and kind of combines them. It's like a combination of CART and Gaussian processes, and it grows and prunes the trees based on some posterior probabilities. That sounds like it's going to be complicated and a lot of work, but it actually goes really fast. And they have a really nice vignette as well for the treed Gaussian processes. So if you're looking at fitting large data or large geostatistical processes, I would look at, I would pick one of these vignettes and practice on the vignette, and then go to your code and try and apply the methods there. So I have a few kind of just notes here. How you want to fit or how you want to model your data is going to depend on, are you thinking about predictions or are you thinking about inferences? I really only covered inference as far as it relates to covariates very briefly, but inference in terms of how well my predictions are doing. Smoothing versus speed. If we smooth over and have fewer bases in our ranking, in our reduced ranked methods, then that's faster, but it's maybe not able to capture some of the variability that we would see. The data size is going to matter in how, in the stationarity aspect of it, in how fast it is to compute, and the method that you're going to use. The bigger the data, you're going to not want to use those that GStat approach or the variogram approach that we were using before. You're going to want to use those ones that I breezed through just a couple seconds ago. And then the spatiotemporal dependence, that's a whole new aspect, and that adds its own element of fun as well. And then there's always more modeling choices. We didn't talk at all about non-Gaussian data. I kept taking the log of the zinc because that was more symmetric and unimodal than the zinc measurements themselves. Other types of dependence structures, other isotropy and non-stationarity assumptions. There are lots and lots of other packages out there that might work better for what you're trying to do, but that can be hard to figure out on your own. And then there's also this give and take for, how simple the model is going to be and how fast the model is going to fit, and then how good it's going to be. And then models and estimation methods are always improving. My favorite package to use was GOR, but that one doesn't even, it's still able, you're still able to use it, but it's being archived. And so it's not going to be updated. And so they're always updating their methods, and based on current work, and then also just based on computational structures, and how R is evolving will depend on how these methods continue to work in the future. Thank you so much again for letting me participate in this session and in this series that you guys are doing. My website is cbarrett.byu.edu, and you can email me. I do have a bad habit of seeing an email, meaning to respond, and then kind of it getting lost in the shuffle of all of my emails. So if I don't respond within a couple of days, but you've sent me an email, feel free to just follow up and send a second email. Hey, just want to remind you about this. And I appreciate that. I try not to do that, but it does happen. Thank you guys again so much.